Hello guys, my name is IBM and I'm still taking you through the past paper questions of magnetic fields and magnetic induction or electromagnetic induction. And I think this is going to be part 33 of magnetic fields and electromagnetic induction. Okay, we are starting with the question 103. You are provided with a coil of wire, a bar magnet, and a sensitive voltmeter. Outline an experiment to verify Lenz's law. Okay, remember Lenz's law states that the magnitude of the direction of the induced EMF is always such as to cause effects that oppose the change that produces it or the change that causes it. So we have a magnet, a bar magnet. So I'm going to just put here my let me start with a coil of wire. So I'm going to sketch the coil of wire. Let me try to see if I can sketch it better. Or you could just sketch something like this. Okay, so this is the coil of wire. You can draw a better coil. I don't know whether this is good, but it's not really looking nice. Let me put an iron core here. I want to draw a better diagram. Okay, I think that one is better. So I'll try to draw a coil of wire there with a sensitive, this is going to be a sensitive meter. Then let this be the coil of wire. So I'll bring my magnet here. Let's say this is south, this is north. Okay, now I can put this in explanation. Of course, we know that when we bring the south pole towards this end of the coil, according to Lenz's law, this end becomes south to oppose bringing the magnetic field. Bringing the north pole of the magnet, and work is going to be done so that the voltmeter, the meter deflects in one direction. When you take away the south pole, this end now becomes north to try and pull back the north pole, because in all cases the induced EMF is always such as to oppose the effect that is causing it. So when you try to take away the south pole, the voltmeter, the meter now deflects in the opposite direction to show that the induced EMF is now trying to oppose or to cause the north pole here to try and attract back the south pole. Okay, so in writing, I will say push a known pole into the coil and observe the current direction. And I observe the current direction. The induced field from the coil tends to repel the magnet. The induced field from the coil tends to repel the magnet. The direction of the induced EMF or the direction of the induced field in the coil can be determined by the right-hand grip rule. The direction of the induced field in the coil is determined by the right-hand grip rule. The right-hand grip rule, of course, where the thumb points to the north pole. The north pole of the coil. So the coil behaves as if it is another magnet with one end north and another end south. This is not part of the solution, but I just added it here to just add spice onto the answer. Then reversing, now try to reverse the magnet direction. Reversing the magnet direction that is taking it away. Taking it away gives an opposite direction on the meter. An opposite deflection or direction. So if you bring the magnet and deflects it to the right, when you take it away, it deflects to the left. So reversing the magnet direction gives an opposite deflection on the meter. That is, the field, the induced field tends to attract the magnet. Tends to attract the magnet. Hence, we conclude that the direction of the induced EMF the direction of the induced EMF or induced current is such as to oppose the change producing it. So that is Lenz's law. So the diagram with the coil says the voltmeter and a magnet in a place, I think those are 2 marks. Then one of these would give you the other 4 marks. Push a known pole into the coil and observe the current. The induced field from the coil tends to repel the magnet. Then reversing the magnet direction or taking it away gives an opposite deflection on the meter. The induced field tends now to attract. The other one was repelling, now it attracts. Hence, we conclude by saying that the direction of the induced current is such as to oppose the change that is producing it. A large horseshoe magnet produces a uniform magnetic field of flux density B between its poles. Outside the region of the poles, the flux density is 0. So outside the poles, the flux density goes to 0. The magnet is placed on a top hand balance and a stiff wire XY is straightened between its poles as shown in the figure. So a stiff wire is straightened between its poles as shown here. The wire XY is horizontal and normal to the field. That means it experiences a force whose direction is given by Fleming's left-hand rule. The length of wire between the poles is 4.4 centimeters. A direct current of magnitude 2.6 amperes passes through the wire in the direction from X to Y. Okay. The reading on the top band balance increases. So if the reading on the top band balance increases, it means the force on the magnet is downwards. The force on the magnet is downwards. That's why the reading on the balance increases. And by Newton's third law, the magnetic force on the wire should be upwards. State and explain the polarity of the pole P of the magnet. So we have said the force on the magnet is downwards, which means that the magnetic force is upwards. By Fleming's left-hand rule, by Newton's third law, the magnetic force is upwards. And if the magnetic force is upwards, yet the current is in this direction here. So first, the thumb should point upwards, and the current points in the direction X to Y. You notice that when you try to use your left hand to make the thumb point upwards, with the second finger pointing in the direction X to Y, the only possible way of having the current flowing in this direction and the thumb pointing upwards is when the first finger is pointing in this direction here, as shown by this one here. So it means the magnetic field is going to be in this direction, making this one north and making this one south. Okay. So I would say that increase in the balance reading implies that the force on the magnet is downwards. By Newton's law, the force or the magnetic force on the wire is upwards. So the magnetic force on the wire is going to be upwards. And then now by Fleming's left-hand rule, the field is from P. So P is a north pole. So P is a north pole. So because the balance reading increases, it means the force on the magnet is downwards. By Newton's third law, the force on the wire due to the magnet should be upwards, which therefore means that if the thumb points upwards and yet the current is from X to Y, twisting your left hand in this pattern here, the first finger is going to point towards this side, which makes this one north and the other one south. So P is a north pole. Calculate the flux density between the poles. So the magnetic, of course, by Newton's third law, the magnetic force is going to be equal to the change in the weight. The change in the weight, of course, this will be B equals to M times G, which means that B is going to be equal to mg divided by IL. The change in mass was 2.3 grams, so that is going to be 2.3 times 10 to the power of minus 3 to change to kilograms, then times 9.81, then divide by the current, which is 2.6, and the length is 4.4. So divide by 2.6 and 4.4 times 10 to the power of minus 2. So 2.3 exponent minus 3, then times 9.81 divide by 2.6 times 4.4 exponent minus 2. So that is 0.197. 0.197 Teslas, which is approximately 0.20. The direct current in B is now replaced by a low voltage sinusoidal current, root mean square value 2.6, that is its alternating. Actually, the variation in the reading of the top hand balance. So we can first of all find the peak current represented by that. So the maximum current is going to be I root mean square times root of 2, which is going to be plus or minus 2.6 root of 2. That is the peak current. And then we know that from force, which is B equals to mg. Of course, the magnetic field is the same. The current is the peak current has changed. So it means the mass is directly proportional to the current because G is the same. So M is directly proportional to current. So I have two equations. I'm going to ignore B, I will ignore L, I will ignore G. M is directly proportional to current. So maximum mass, which I'm going to call M maximum, or peak value of M for alternating. The peak value of M, I'll call it M naught, is equal to a constant times the current to peak current, which is 2.6 root of 2. Then for the other one, the mass was 2.3 grams. That is also equal to a constant times the current was 2.6, which means that the peak current, the peak mass is going to be just 2.3 grams times root of 2, which gives us plus or minus, because the peak would be positive or negative. So this is going to be 2.3 root of 2. That is 3 point. Okay. Total change. I'll first ignore this. So the peak mass is going to be plus or minus 2.3 root of 2 grams. So total variation is going to be plus 2.3 root of 2 minus negative 2.3 root of 2, which is the same as 2 times 2.3 root of 2, which is going to be 2.3 times 2 times root of 2, which is 6.5. So this is total change is going to be 6.5 grams. This was plus or minus 2.3 grams times root of 2. So total change is going to be 6.5 grams. A small coil is positioned so that its axis lies along the axis of a large bar magnet, as shown in the figure here. Its axis lies along the axis of a large bar magnet. The coil has a cross-sectional area of 0.40 centimeters squared and contains 150 turns of wire. The average magnetic flux density B through the coil varies with the distance x between the face of the magnet and the plane of the coil, as shown here. Okay. The coil is 5 centimeters from the face of the magnet. Use the figure to determine the magnetic flux density in the coil. So it's 5 centimeters, so I'll have to check 5 centimeters from the graph. 5 centimeters. I think 5 centimeters corresponding to this here, which is, this is 50. So B is 50, magnetic flux density is 50 milliteslas, or it's 50 times 10 to the power of minus 3 teslas, or you could write 50 milliteslas. Hence, show that the magnetic flux linkage of the coil is 3.0 times 10 to the power of minus 4 Weber. So we know that flux linkage is equal to NBA, or band. So this is number of turns, 150, then area is 0.40. So this is going to be 150, 150 times 50 times 10 to the power of minus 3 times the area, which is 0.4 times 10 to the power of minus 4. So now our calculator, we have 150 times 50 exponent minus 3, then times 0.4 exponent minus 4. We have to change the area to meters squared. So this is giving us exactly 3.0 times 10 to the power of minus 4 Weber. The coil is moved along the axis of the magnet so that the distance x changes from x equals to 5 centimeters to x equals to 15 centimeters in a time interval of 0.3 seconds. Capture the change in flux linking the linkage of the coil. So up to x equals to 15, and 15 is this one here. 1, 2, 3, 4. I think that is 4 times 2. I think this is 8. So we want the change in flux linkage. So the change in flux linkage is going to be equal to N times change in B, then times the area, which is going to be 150. Change in B is now 50 minus 8 times 10 to the power of minus 3, because it is from 5 to 15, that is 50 to 8. Then this is going to be times the area, which is again 0.4 by 10 to the power of minus 4. We shall check this again. 150 times, I think this is 42, exponent minus 3 times 0.4 exponent minus 4. That is 2.25 times 10 to the power of minus 4. Sorry, 2.52 times 10 to the power of minus 4. Then the average EMF induced in the coil. Average EMF induced in the coil. So we know that the induced EMF is equal to the rate of change of magnetic flux linkage, which is going to be the change in the flux linkage divided by time. So the change is going to be 2.52 times 10 to the power of minus 4. The time it takes to change is 0.30 seconds. So that is 8.4 times 10 to the power of minus 4 volts. State and explain the variation, if any, of the speed of the coil so that the induced EMF remains constant. We want the induced EMF to remain the same as that. So state and explain the variation, if any, of the speed of the coil so that the induced EMF remains constant during the movement in C. So we know that induced EMF is equal to the change in flux linkage divided by time. And we know that time equals to the distance, which distance is going to be now x, divided by the speed. So it means the induced EMF is going to be equal to change in flux linkage. Then I'm substituting where there is time, I'm putting distance x over speed. So this is going to be times. Now this is going to be time is distance over speed. So this is going to be speed over distance. So this means that as distance x increases, the flux linkage decreases according to the graph. That means if we want the EMF to remain constant, then the speed must be increased. From the graph, we notice also that as x increases, we notice that the graph is becoming horizontal, which means that the change in magnetic flux linkage decreases as x increases. So if because the change in magnetic flux linkage decreases as x increases, to maintain the same EMF to be induced, then the speed must increase, as established or as seen from this expression here. Change in EMF is change in flux linkage over time, but time is distance over speed. So which means that EMF is change in flux linkage times speed over distance. And as x increases, we have seen from the graph that the flux linkage decreases. So that means if we want to maintain the same EMF, the speed should increase to compensate for the decrease in the flux linkage. Therefore, put this in writing, we shall say that for a small change in distance x, change in flux linkage decreases as distance x increases. As distance x increases, thus speed must increase to keep the rate of change constant. Alternatively, we have said the change in flux linkage decreases as distance increases. Alternatively, we have said that change in flux linkage decreases as distance x increases. As distance x increases, and of course at constant speed. If the speed was to be constant, at constant speed, if this was to be constant, when this becomes bigger, this one becomes small, this is going to become small. So if the speed was to be constant, the EMF or the flux linkage, the EMF, or you could say flux linkage, decreases as x increases. So the speed must increase to keep the rate of change constant. So the speed must increase to keep the rate of change constant. So because the EMF is equal to the flux linkage over time, and yet time is distance over speed, if the speed remains constant, increase in distance means a decrease in flux linkage, so the EMF will be decreased. So if we don't want the EMF to be decreased, then the speed must be increased to compensate for the decrease in change in flux linkage. Okay, so I want part 33 to stop there. See you in part 34. Until next time, bye-bye.